everyone. This is Honey the Kids Try Crypto. So a little quick disclaimer. I'm going to be doing a live demo where I skim your credentials if you have them. So if you have ICT mobile credentials, you might want to turn off the proximity and shake to unlock features in the mobile app. So today we're looking at the research that I have done into the ICT access control system over the past year. We're specifically looking at four main things: how there are default pre-shared keys in there, and how we can use that to clone DESFire credentials and Bluetooth credentials, and then how we can use a cipher block chaining type of exploit to take credentials and then privilege escalate and elevate our privilege into other rooms we shouldn't be able to access. How we can exploit the predictable random number generator on the readers to allow us to present fake credentials without knowing any of the encryption keys. How a weak key negotiation can allow us to tap the controller-reader communications, and we can read card numbers out of that and inject our own as well. The recommended mitigations for these if you implement a system yourself, and also if you're an ICT installer and want to fix these problems. Oh, okay. And also an exciting bonus if there's time. So a little bit about me first. I'm a computer engineering student here at UC. I'm a little bit of an amateur hardware hacker, and I play a lot of CTF, and apparently I'm really good at it. So about ICT. So they're a company founded in 2003. They manufacture their access control systems here in New Zealand, and they've basically make this TSEC line of card readers. So they've got them in white and black and all the different shapes and sizes, with and without pin pads. So you can see one there, a white one with a pin pad, and then we've got this sideways mounted one, which apparently they mount them sideways. So at a high level, what a card reader does, if you've never seen one, is it takes in a physical card or a mobile credential or some way to present yourself to the card reader, and it's going to look at all that data, check if it's valid. It also will cram down multiple, if it's a physical card mobile credential, the controller in the back won't know. It will just get your card number and your facility code, which identify your card, and send that back to the controller, and then your controller will sit there and give the final yes/no if a door should open or not. So TSEC readers accept two main type of credentials. So you've got the physical cards. These are your 125 kilohertz cards, which are insecure. These, they're really insecure. They just power up and spit out the card number. There's no cryptography there at all. MIFARE Classic, this was secure if this was 20 years ago, but their cryptography has since been broken, and it's relatively easy to clone these cards. And then we've got ICT secured MIFARE, which takes the data that will be traditionally stored in the MIFARE Classic card and just puts another layer of AES encryption on that. Problem with this is you can still just grab that data in the card if you have a card and just clone it into another card, as long as you use those magic cards, which clone the UID as well. And then there's MIFARE DESFire, which for the most part is secure, just we'll get to the little asterisk there in a bit. And then there's the mobile credentials, which are an ICT custom solution which can present your credentials over either Bluetooth or NFC, or they in their documentation sometimes call it that ISO standard. So in the cards, there's this thing called a credential blob. This is mainly used on the newer technologies like your DESFire, secured MIFARE, NFC, and Bluetooth. It's just a way for them to encrypt your card number and site code, which is encrypted with AES-256 CBC. So they'll store your card number site code in the traditional Wiegand format, which we allocate about 8 or 16 bits depending on the flavor to the site code, and then 16 bits to a card number and 2 bits for parity. And these cram to 4 or 5 bytes inside a 16-byte payload, which is just padded with other data to let the reader understand more about that credential. So DESFire is a card technology developed by NXP. It's currently one of the most secure ways to store information within a card. without getting into like the asymmetric cards with PIV and like scanning YubiKeys on readers and stuff like that. It uses a mutual AES authentication, although it does have DES in the name. Most of the time they just use the AES functionality in it and rather than the DES because it's much more secure that way. But for this mutual authentication, you're going to need a key to somehow authenticate with the card. So there are two ways we can grab a key. So we can have a static key which doesn't change between the cards. The problem with that is if someone manages to read the key out of the card, maybe they like etch the chip out of it and read out the EEPROM by eye or something like that, they've essentially attacked every single card. They can then issue their own cards and all the stuff like that, which you probably don't want. So what we use instead is a derived key. So how derived key works is we're going to take some unique data about the card, say the card's UID or unique identifier, which is well known because the card just gives it away for free when we power it up. And then we're also going to take a base key. So this is a secret which it would be kind of like a static key, but this key diversification runs in the reader so that the card key is never presented outside of the reader. And so with this card key, we can do the authentication, grab our credential. But the one problem we've got is this base key. So where does it come from? So this is where we lead into our first issue with the system or vulnerability, where these keys are just held in the firmware. This is an excerpt from the Ghidra decompilation I went through, long and tedious, and those are redacted encryption keys. And yeah, so these are held in, they tried to hide them. They're encrypted in the firmware, but there's an adjacent encryption key in there, which if you just extract that encryption key, you can recover these keys really easily. So hiding them this way isn't that great. We'll get to mitigations in a bit, but this is security by obscurity. So ICT have acknowledged this issue. Every time you try purchase cards from them for a new site, they also do cite this, so they're doing good in that way to get you to use like the more secure technologies. And so if you want to mitigate them, if you're an ICT or if you want to mitigate these risks, if you're an ICT customer, ICT say that you should be using like card and PIN on your doors. If like they're external doors, once you're inside with a card, it's pretty secure in that way because you've already authenticated the card. And then there's also using the custom key sets as well. So you can have your own keys for your site. As for general mitigations, if for some reason you need to have default encryption keys, you should really be avoiding symmetric encryption because in this way, with having the symmetric keys, the reader can issue credentials, which typically we don't want. You should have a central authority be doing that rather than the readers. So using something like an RSA or elliptic curve keys for that would be much better. And then you should be able to like replace the keys or roll the keys. So in case they do get compromised, it should be relatively easy to roll these keys and switch them out. And there's also the using just a TPM or a hardware module or something like that to make it much harder to access the keys, because I was able to read the firmware out of these readers just because it was a relatively difficult process. But with the TPM, it's significantly more difficult. Like, they're designed to be hardened. Their only job is to do crypto. And so yeah, now we're going to take a little bit of a pivot into their Bluetooth credentials. So these perform similar to a DESFire key negotiation or authentication sequence between the phone and the reader, this time over Bluetooth. The thing about this is if we know the encryption key, we can pretend to be a card reader. So in an older version of the app, we were actually able to just force the usage of a default key, but that's since been removed. And yeah, if you have credentials now, you should turn them off if you haven't already, and we're going to see if the live demo works. So I've got this little Python script I wrote a few days before coming here. Apparently it should work. It might not, we'll see. When the mobile credential decides to open, my phone's set for shake to unlock, and if I give it a shake, it might come and spit up credential stuff. Oh, here we go. And we have Credential. So, well, here's all the information. If you want to clone this credential, have fun. But, oh, what's the number there? Oh, is it going to open the slides back? Okay. That one? Oh, okay. Hold on. Here was backup plan if it didn't work. So yeah, what would happen with this is just running this on a computer is practically useless, but you could deploy the sort of same code base on like a little ESP32 and hook it up to a coin cell battery and basically just throw these around sitting next to card readers or in an office, and you could just passively skim people's credentials as they walk by, because their phone's just going to spit out the credential whenever it sees the right like Bluetooth device sitting in the area. It's just going to spit out its credential to it. And, well, yeah, you could really easily get a load of credentials like that. And so we're going to look now at the NFC protocol. This is much simpler than the DESFire one or the Bluetooth one. There's just a little bit of AES encryption here and a 32-byte payload. So protocol looks something a little bit like this. You put your phone in front of the card reader with NFC. The reader's going to say, do you support this application? Oh, okay, what's happened? And then it's going to say, yes, and here's my mobile credential data, and that's it. So your mobile credential data looks a little bit like this. So here's another mobile credential if you want that. So here's 32 bytes. If we run it through the AES-CBC decrypt function, we get all this data. So that first half is practically discarded. It doesn't get validated in any way. But then this entire second half of the credential is what's important. So this is a credential blob. The last 5 bytes are really the only bytes we care about. These encode that credential you see on the bottom of the screen, like facility code 60419 and card number 83. So CBC stands for cipher block chaining. And so this is a diagram I ripped off Wikipedia. It's really helpful. So what happens is AES is a block cipher, meaning it'll only take, it doesn't work with variable sizes. It only allows you to encrypt 16 bytes at a time. And so what happens is we're going to run the thing through a CBC decrypt. And we don't actually care about the first block of plaintext. We've just got that little red cross thingy there. But what happens is that second block, the plaintext is XORed with the ciphertext. This is typically used for when you've got lots of data in an order, so you can't start reordering the blocks. But in this case, it's to our advantage because it allows us to just XOR with that credential blob with those 5 bytes that we know to allow us to privilege escalate. So this is where we come to vulnerability 2, where if we know the card data by, say, giving it from a mobile app or like skimming someone's DESFire credential if you know the keys, or even like NFC, their NFC credentials, you could pretend to be one of them. You don't need any keys for that. If you know all that data and you know the card number, because that's given to you in the mobile app as well, and you know a target card number you want to go to, which they're typically sequential, so you can just increment your card number or decrement or try card number 1 or something like that. You can then manipulate your credential into whatever you want, really, and you might be able to get privilege escalation, who knows, or maybe you're the CEO and you want to pretend to be someone lower. Yeah, so for mitigations, if in general you want to validate all the data within your payload, so you could run this through like a SHA checksum or a CRC checksum, but as long as it's reasonably difficult to like mess with the data in a way that isn't going to be picked up, you should be fine. And then, but for ICT equipment, I don't know of any mitigation other than disabling NFC. So you should probably disable NFC if you have ICT card readers. Okay, now we're going to look at the DESFire authentication from before. So basically how this works is when we present our card to the reader is going to request to authenticate with key number 1. Then the card's going to respond by generating a random number, then encrypting it with this, with the encryption key number 1. Then the reader's going to respond by generating its own random number and encrypting this, as well as shifting around the data in random B, which is what the little prime means. We're going to take the first byte of the data and shove it on the end. That's just so we can't reuse the same block that the card sent us. And then we're also going to use an IV of the previous data, so that's the encrypted data from before. And then finally, or what the card's going to do then, is it's going to validate that the random B prime is exactly what it expects random B prime should be, because if you don't know the key, you're not going to get that same encryption done properly. And then finally, the card's going to respond by sending over random A prime, which is again shifting that data around. And then the reader's going to validate if the card sent the right data over. And from that, we can derive a session key, taking those two random numbers and just taking little parts and mushing them together. And from that, we don't need to know that encryption key anymore. We've authenticated with the card's satisfied that we're happy, and also the reader's satisfied that we've got a session going. But the problem with this is, let's suppose we're an attacker and we want to be the card. That's what this little red box thing is. That means we also know what random B is. And let's also suppose that the random number generator on this thing is weak, which it is, which means we'll also know random A. And so in the encryption stage, what we can do is we know random A here, and we also can control this previous data that's come over from the reader. And if you recall back from a few slides ago, the CBC thing, this IV gets XORed with the plaintext of random A. So this gives us an encryption primitive, which will allow us to then forge this entire negotiation with the reader. So that means we can then pretend to be a reader. So also, that random number generator on the reader, that only has 8,000 unique values that it will generate. So that's pretty weak. And so for the vulnerability 3, yeah, we know that random A through a weak random number generator. Random B is attack controlled, and we have that encryption primitive. So then we can forge an authentication session, and then we can get session keys without knowing the app key, which will allow us to then present credentials to the reader without knowing any of the keys. So as for mitigations, on TSEC, this attack is completely impractical. It takes you 3 hours holding a Proxmark or a flipper up to a card reader, which you might be able to do in the middle of the night. Who knows? And then and just in general, you want to just seed your random number generators properly. Make sure they're difficult to predict, and make sure they've got really large cycles. Yeah, because 8,000 is relatively small in the terms of like 2 to the 32. That's pretty small. And in ICT are working on an update to fix this, I think. I hope so. So there's currently no mitigation, but you should update your firmware when an update comes out. So we've looked at getting data into the reader, but what about getting data back to the controller? So for this, there are 3 ways. You've got Wiegand, which is just no encryption. It's a de facto standard that came around from just readers in general. I think it dates back to like the HID days, or even before that, probably with Magstripe. Don't quote me on that. So there's no encryption on there. It's just 2 wires that go back to the reader, and when there's a 1, one of them will go low, and when there's a 0, the other one will go low, and it just keeps signaling like that. There's no encryption there. It's relatively easy to tap, and that avenue's been discovered before and explored before. Then there's OSDP, which is like the Open Supervised Device Protocol. This is like the industry standard, essentially. Like your new inner range readers use it. Pretty sure a lot of the new HID readers use it. It's like really, really secure. It uses AES authentication. I personally haven't looked into it yet. I plan on doing that soon. So for what I can say is it seems secure, but I don't know. But then there's the ICT Smart Protocol. So this is a proprietary protocol that goes between the reader and the controller, and I also think between all the modules in their controller. Don't quote me on that either. But essentially what we have is, with this, you need to somehow negotiate keys between the reader and the controller. So what we can do there is, or what happens is the controller sends out reset state, reset state, reset state over and over until a device appears and it notices it appears. From there, the controller is going to send over some random data. So this is just a random number. The controller that I've looked at seems secure in the random number generator. It's just using the Windows CE inbuilt random number generator. I think that's secure. And then the reader's just going to respond with its serial number and some other data as well that I didn't bother to put in there. But then from that, you could derive a few encryption keys, and then they establish common keys and get encryption going between the devices. Problem is with this, if we can watch the negotiation from the start, we can watch all the communications that go through. And so what we could do is we could do false injection on this, right? We've got this reset state. So what would happen if we sent a reset state? Apparently the reader decides to respond to that and reset its state. And then when the controller tries to poll the reader for any data, it's going to basically it's going to reset it again, and then it's going to set up a session for us to watch. So this is kind of like a Wi-Fi DEOS attack. And so, yeah, this is where we come to vulnerability 4, where if we can intercept the keys directly from the start, we can follow the conversation entirely. And then we can use false injection to renegotiate those keys, and then follow conversations. That would allow us to intercept card numbers, people's PIN numbers they type in. We could also control the buzzer if we wanted to, or flash the lights on it. So as for mitigations, really don't roll your own crypto. If there's anything you get away from this talk, don't roll your own crypto. Use TLS. TLS is specifically designed for this stuff. I think I can say this. Gallagher uses MTLS on their RS-485 bus, which is stripped down, or they've just removed a bunch of ciphers that seem insecure that they didn't want to implement on their 485 bus. But yeah, if you really need to roll your own crypto, you should use an established key exchange algorithm like a Diffie-Hellman. Don't try building your own, especially with symmetric secrets. If you can grab those symmetric secrets, you can derive whatever you want from them. And so while we have this little statement from ICT, ICT appreciates the clear and concise manner the information has been provided in and remains committed to improving their product security. And then we have code execution on the card reader, which is always fun. So here's a little video. Yeah, I remember getting this working, and it was 4 in the morning. Yeah, so... So this isn't just playing Megalovania on the card reader. This has much wider... Oh, where's the slides gone? Oh, come on, it sent me to the start. Where are we? Here. Here we go. Yeah, so this isn't just playing Megalovania on the card reader. This is, you could install a skimmer into the reader. You could grab your pins and cards, everything that you'd want from the reader. But yeah, this is a really cool exploit chain. So basically, how it works is when we power up the reader, or we can reconfigure the card reader in a special way to allow us to perform this buffer overflow into some protected parts of memory, or supposedly protected. And the problem is, to reconfigure the reader, we need to scan a special card in the first 2 minutes of power up. So there happens to be this way to trick the processor in it to rebooting it by locking the entire thing up. And so you can do that with sending a few special packets to the reader, and it sits there waiting for a response, and if you just don't respond, the reader reboots. And then we can scan a card to allow us to perform the buffer overflow. And well, because there's no ASLR or other protections on an ARM-embedded system, it's relatively easy to just overflow a function pointer, which points back to our buffer that we filled with code, and we can run the code and win. And so, well, if you want to patch your firmware, currently you need to explicitly request these firmware files from ICT support. Throughout the research process, I managed to get my hands on a copy of the firmware through an official source, one of their OEM partners who published the firmware on the website, but after I told them about it, they pulled it, which isn't fun. And well, also, if you're updating the firmware, you need to use this a clunky program, and you need to remove the readers from the walls, wire them into your computer, do a few power cycles. It's a very laborious process, but I've been told that in a future update, they're going to allow you to perform updates directly from their controllers, but only if you're on the ICT 485 bus. So for scale, though, I pulled this out of the tender for when they were doing University Canterbury upgrade from Cardax to Gallagher. Here there are 1,300 doors, and those are 600 card readers. If you think each of those takes 20 minutes to update, there's a lot of labor involved with that. So yeah, in conclusion, don't roll your own crypto. Thank you.
All right, thank you. Remember, kids, don't do crimes.
Busted.